EM algorithm, expectation maximization. Before we proceed with the EM algorithm, this is Jensen's inequality, a well-known inequality that we need to understand because we're going to use this result in our derivation. So we have the log function. The log is a concave function, and Jensen's inequality holds in this manner for concave functions. So we have weights wi greater than or equal to 0. I is an index, 1, 2, 3, 4, up to some value, and summation I equals 1. So the sum of all the weights is equal to 1, and each of those weights is greater than or equal to 0. And so log summation of wi xi is greater than or equal to summation I wi log of xi. That's Jensen's inequality. So what we are doing is log of the summation, we take the log inside the summation and we move the weights outside the logarithm. So it's wi then log of xi. And I've shown this for w1 and w2 each being equal to 1. So when w1 and w2 are equal to 1, what do we have? Log of summation wi xi is, instead of xi, I have x and y. So I have x and y, and wi is half. So summation wi xi is this point. And this is the log curve. This is x and y. I have log x and log y here. And since this is the midpoint, x plus y over 2, this is log of x plus y over 2. That's the left-hand side. And now summation wi log xi is, since each wi is half, this will be equal to half log x plus half log y. So this is log x and this is log y. We draw this straight line here joining these 2 points, x log x and y log y, and we take the midpoint of that. This midpoint is half log x plus half log y. And you can see that log of x plus y over 2, which is this, is more than half log x plus half log y, which is exactly what the Jensen's inequality says. So now the EM algorithm. The EM algorithm is similar to gradient descent, and so let's see how it works. It's an ascent algorithm since we are trying to maximize something, and so let's see. Our goal is to maximize a concave function f of theta, and so this is what we have to do. Theta hat is our estimate of theta, that's equal to argmax with respect to theta of f of theta. And let's denote at iteration I our solution as theta superscript I. So it's an iterative process. And what we will do is we will construct a lower bound function Li of theta. Since you have the superscript I appearing in this lower bound function L, we have to construct the lower bound function every iteration separately. So a lower bound function, so this function Li of theta is a lower bound of f of theta. Therefore, Li of theta should be less than or equal to f of theta, because that's the definition of a lower bound function. And so Li of theta is our estimate of f theta. Excuse me, lower bound of theta. And now at theta I, at that particular iteration, theta I is the current model that we have. And if you plug in the value theta equals theta I in the lower bound function and the original function that we want to maximize, then this less than equal to is replaced with a strict equality sign. So Li of theta I is equal to f of theta I. In other words, at theta I, the lower bound function and the function f that we are trying to maximize, they coincide, they touch. At every other theta that's not equal to theta I, Li of theta is less than equal to f of theta. So this is important to remember. It's a lower bound. Li of theta is a lower bound of f, and at the current guess theta I, the current estimate in iteration I of theta, the value of theta, the lower bound and the function f have the same value. So this and this are two important things to remember. And so then what we do is we assume that this is f theta is hard to maximize for some reason, as you'll see later, but it's easy to maximize the lower bound in closed form. It's available in closed form, and so you can derive an expression for its maximum. And so we maximize, instead of maximizing the concave function, every iteration we maximize the lower bound Li of theta. So that maximum gives us the next iteration. So theta I plus 1 is our next estimate of theta that we're trying to guess. That will maximize this concave function, and so theta I plus 1 is argmax of Li of theta. Instead of doing this argmax, which is hard to do, we do this argmax iteratively, and we proceed through several iterations, and gradually this theta will converge to theta hat, the maximum of f of theta. So this is how this EM is a coordinated ascent algorithm. So this is the function f of theta. This is the x-axis is theta, and the y-axis is f of theta. And so we want to maximize f of theta. In fact, this is the maximum somewhere around here. And so we are looking for, this is our solution that we want to reach. Now in iteration I, this is what we have. Theta I is the value. And in iteration I, and this is f of theta I. And so what we do is we construct a lower bound L superscript I of theta. And remember, the superscript I of theta, L superscript I of theta, excuse me, needs to have two things. It has to be a lower bound. So it has to be lower than this f of theta curve, this blue curve here. So the Li of theta has to be lower than this, and it has to touch at this red point, because at theta I, the lower bound has to be equal to the function. So this is what the lower bound looks like. Li of theta is this dotted blue line, and it's at theta I, Li of theta I is equal to f of theta I. Both of them, so it's touching right here, and it's right here, they're touching, and at every other place, the lower bound is lower than f of theta. So these are the two things. And so once we construct the lower bound function, assuming that it's not so easy to maximize f of theta, what we do is, in that iteration, we maximize the lower bound function instead, Li of theta. And so we maximize this blue dotted line, and so that gives us this. Theta I plus 1 is the maximum of Li of theta. This is the maximum, and this is the argmax, and this gives us the estimate theta I plus 1 for the next iteration I plus 1. So now let's begin with the EM algorithm in earnest. And so let's look at the hidden variable, the role of the hidden variable first. Now, what EM algorithm does is when you cannot apply a log likelihood to get the maximum likelihood estimate, because even after taking the logarithm, it's not mathematically tractable. That's when you, in order to maximize the likelihood or log likelihood, you can apply the EM algorithm. So what you have is data which is drawn according to some probability distribution, and so theta is the set of parameters of the probability distribution, and that's what we have to estimate from this samples of this random variable x. So what we assume is that there is some hidden or unobserved or latent variable z, and that z in the example that we took earlier, the motivating example, the biased coin problem, was whether it was coin 1 with the probability of heads of p1, or whether the coin was coin 2 with the probability of heads p2. And so the hidden variable, we'll denote it as z. And so this random variable x, which is generated using this probability distribution, actually contains z also. So this theta, the PDF, the probability distribution, generates x and z, but the z's are hidden from us and only x is available. So that's the hidden variable z. And so what we have to do is, this is the log likelihood, and our goal is to find the maximum of the log likelihood. So we want to find from the x's the samples of the observed variable x, several samples. We want to find the max likelihood estimate of theta. And unfortunately, this L is not very easily tractable from a mathematical standpoint, and therefore we apply the EM algorithm. So what we will do is we will find the lower bound estimate of this log likelihood in each iteration. That's the first step of the EM algorithm. So at each iteration of the EM algorithm, the solution is theta superscript I, and we'll define a conditional distribution QIZ on the hidden variable z, and that's given by this expression. Q superscript IZ, that's the conditional distribution on the hidden variable, is equal to, by definition, PZ given x theta I. So given the current value of the parameters, which is theta I, and the data x, the condition on that, what's the probability of z, that's the conditional distribution QI of z. And this is, using Bayes' rule, this is equal to P of the joint probability x comma z given theta I divided by summation P x comma z given theta I. This denominator is actually simply equal to P of x given theta I. So theta I. So this is the denominator, and so this is the numerator is x comma z, and the denominator is p x, so that gives us probability of z alone, and that we call a qi of z. And now since Qi of z is the probability of z, and so for all possible value of z, if you sum the probabilities, then you should get unity. And if you recall the biased coin example, the fraction f1 and the fraction f2, which is the probability of the coin being coin 1 and the coin being coin 2, if you add them up, you get 1. F1 plus F2, and so in this situation, summation Qi of z is equal to 1 because it is a probability distribution. And let's remember Qi of z because we'll be needing it several places in the derivation later on. So Qi of z is the probability distribution of the hidden variables conditioned on the current model parameters or current hypothesis. I can use the word hypothesis here, and the observed samples. So now we proceed to derive an expression for the lower bound of the likelihood L, uppercase Lx given theta. So at any iteration I, the solution is theta superscript I, and so the lower bound of the log likelihood, which is uppercase Lx given theta, is this. Li theta is the lower bound at iteration I, and that's equal to summation z over all values of the hidden variable Qi of z log px comma z divided by Qi of z. So this is the lower bound estimate of Lx given theta at any iteration. And so in order to show that this is indeed what we want, the lower bound estimate, we have to show two things. First, we need to show that it is indeed a lower bound, that is Li theta is always less than equal to Lx given theta. That's what we have to show, and that's the first thing that we have to show. We also have to show that so that's the first part. So we also have to show that at the current estimate theta I, the less than equal has to be replaced with an equality. So the lower bound estimate touches the original function, the log likelihood L, at theta I. So this is the second part, and we have to show both these parts. So first we will begin with showing this, and then we will show this. So the first part, this is the expression for the lower bound Li theta, and what we need to show is the first part, which is that it is indeed a lower bound of the log likelihood Lx given theta. And so now this is the log likelihood Lx given theta is log of the probability of the samples, the samples that were observed given theta. By definition, that's the log likelihood, and that's equal to log of summation z, since z is unobserved, so we have to consider all possible values of z, and so this is equal to log of summation px comma z given theta, which is equal to log of, now I take this probability and I am multiplying and dividing it by Qi of z. So this is what I have, and let's see. Now I'll apply the Jensen's inequality. So what I get is, now treat these as the weights. So log of summation wi, and this is the xi, log of summation wi xi is greater than equal to summation wi log of xi. And that's Jensen's inequality, and so this is what we get. So from here, so this is greater than equal to, and so since we started off with Lx given theta, the log likelihood, we just showed that the log likelihood is greater than equal to this, and if you compare this expression, this is the same as this expression. Summation z qi of z log pxz given theta divided by qi of z is in fact the lower bound function. Therefore, we showed the first part that this is the lower bound of Lx given theta. Now we proceed with the second part, which is when theta equals theta I, the lower bound estimate L I theta I should be equal to the log likelihood. So we just make a note that we have indeed proved the first part. Now we proceed with the second part. Okay, so now we need to show the second part, that is at theta I, the parameters or the hypothesis in iteration I, the lower bound, lowercase l superscript I, is equal to the log likelihood at theta I. And that's the second part. Now before we proceed to prove this, let's establish one little expression. So this expression here, pxz given theta I over qi of z, let's evaluate that. First of all, this is the same as this expression here, except theta has been replaced with theta I. And so that's the difference. Theta is replaced with theta I, and now keep in mind that qi of z, we saw that that was the conditioned probability distribution of the hidden variable z. So that's the definition of qi of z, and if you plug in the value of qi of z, then what we get is this simplifies to px given theta I from Bayes' rule. So this expression here, when we replace theta with theta I, this what's inside the log becomes equal to simply p of x given theta I. So let's keep this aside, this inequality, excuse me, this equality that we just derived, and now we will proceed to show the second part. So the lower bound Li at theta I is, by definition, this is Li of theta, and I've replaced theta with theta I here, and so this is equal to, if we use this expression that we just derived earlier, then I replace this what's here with p of log, log p of x given theta I, which is equal to, since this log does not contain z, so I can take it outside this summation, and so that's equal to log p x given theta I times summation z qi of z. But since qi of z is the conditional distribution of the hidden variable z, summation z is summation z of qi of z is 1, and so what we are left with is simply log px given theta I, which is equal to, by definition, that's the log likelihood. So these two we showed are equal. In other words, we showed that at theta I, the lower bound is equal to the log likelihood, and that's the second part of our proof. So just to summarize, at iteration I, the solution is theta I, and this is the lower bound function, and we showed that Li theta is less than or equal to x theta. So it is indeed the lower bound, and it touches the log likelihood at theta I, and so we can apply the Ascent method that we had discussed earlier to the lower bound function. So we have now derived an expression for the lower bound of the log likelihood, and we can now proceed with EM. But can we simplify this lower bound further? So let's try to simplify before we implement the EM algorithm. So this is the expression for the lower bound, summation qi of z log pxz given theta over qi of z. And now this log of numerator divided by denominator is equal to log of the numerator I've taken here, and then minus log of the denominator. So I've divided this into two terms, summation z qi of z log pxz given theta minus summation z qi of z log qi of z. And noting that qi of z is a probability distribution, this looks like an entropy term. Just an observation which we do not use here. Okay, so this is equal to, the first term is uppercase Q, we call it the Q function, Q theta comma theta I. So this Q function is given by this expression. That's the first term of our lower bound, and the second term is HQI of z. Now HQI of z is independent of theta. Well, it does depend on theta I, the value of the parameters at the current iteration, but it does not depend on the variable theta itself. And so when we maximize the lower bound in EM, we don't need to consider this second term HQI of z. So in other words, since it's independent of theta, we don't really care about this term when we do the maximization. We only focus on the Q function, Q theta comma theta I. And so this is the lower bound, and we just showed that the lower bound function has two terms, Q theta comma theta I and this, and Q theta comma theta I is given by this expression here, and this is the simplified lower bound that we need to maximize in each iteration of EM. So the maximization step of EM is given by this expression here, theta I plus 1. The hypothesis for the next iteration is argmax of Q theta comma theta I, where Q is given by this expression here. So now let's write down the EM algorithm as coordinated ascent. Okay, so this is our goal, to maximize the log likelihood, and what we do is we implement an iterative process, and in each iteration the solution is theta I, and then we construct the Q function. Instead of the lower bound function, we construct the Q function, and since the maximum of the lower bound will be equal to the maximum of the Q function, the argmax of the lower bound and the argmax of the Q function will be equal. Therefore, our next estimate, we let theta I plus 1 equal argmax Q theta comma theta I. That's the maximization step. Now, everything good, but we still haven't figured out how to deal with Qi of z. So let's look at the Q function. This is the definition of the Q function, and it's Q theta comma theta I. It's given by summation z Qi of z log pxz given theta. And qi of z is a probability distribution, the probability distribution of the hidden variable z. So this is the definition of qi of z. It's p of z given x given theta, x comma theta I. So since qi of z is a probability distribution and summation qi of z is equal to 1, we have already seen that. So this expression here, if you take summation z of any probability distribution times some function, then this is nothing but the expected value of that function under this probability distribution qi of z. So in other words, we can write q theta comma theta I as the expected value of log p x comma z given theta when the hidden variable follows this distribution p z given x theta I. So this is what we want to maximize. The log likelihood is being maximized. So in each iteration, theta I plus 1 is equal to argmax of this expectation that we just saw, which is the same thing as the q function. The q function is in fact an expected value of the log pxz given theta. Now the question is how to find this expected value of this log. How does one find this? Now if you look at this distribution, z follows this probability distribution. It's this here, which is probability of z given the observed x and theta I. And so since we know both of these, x are the observed variables and observed samples of the variable x, and theta I is the current value of the model parameters, and so qi of z, which is this probability distribution, can be computed directly from those known values. So the hidden variable z can be estimated from samples x and theta I. That's the E step of the EM algorithm. So we write down the EM algorithm. So current iteration is theta I. E step, we find the probabilities of the hidden variable z from the observed samples and theta I. And then we apply the M step. The M step is to obtain the maximum likelihood estimate theta I plus 1, which is equal to argmax of this expected value of the Q function. With this, we end the derivation of the EM algorithm.